Hi, welcome to a deep dive into asynchronous Rust. I'm Herbert Wolfson with Arden Labs. I'm here today in the studio in Miami, rather than my usual basement with a squeaky chair. So hopefully sound quality and lighting is going to be better today. We're going to be talking about asynchronous Rust. People often talk about there being a synchronous Rust and an async Rust and never quite sure the twain meet. Well, that's not entirely true. They can talk to each other, they can work together, they can help you build a really high performance server architecture that takes advantage of both. So using threads, you can achieve very low latency, high performance processing. Using async, you can take advantage of the latency of people connecting in, waiting on databases, waiting on disk, waiting on other services to execute. Async can pull that together and maximize your CPU usage overall by maximizing the effective throughput of the connectivity. By joining the two together, you can make some of the fastest and most responsive server systems out there. And so today we're going to be doing a dive through, starting at the very beginning of what is async, how do I use it, how do I connect to it, all the way down to some of the more convoluted parts where how do I talk between async tasks, how do I queue channels, how do I persuade things to stay in the same place in memory so that the rest memory model still works, but you get all the benefits of an asynchronous environment. All right, let's go ahead and start with the all of the code that we're using today is available for free on my GitHub at the URL that's listed, and hopefully posted in the hopefully going to be posted in the description for the video or the comments. Because we've got a lot of content to do today, I'm not going to be live coding all of it in front of you. I'm going to be showing you code on the screen, talking you through it. I recommend pulling up that GitHub, cloning it. It's full of useful examples that can act as templates for the code you need to write, get you up and running with async very quickly. In detail, we are going to cover threads versus async, together or separate. What is each? How can they work together? How they interact. Async runtimes, which are broken up into executors and reactors that handle making async actually work in Rust, and why Rust took the decision that the runtimes themselves aren't part of the language. We're going to have a look at a couple of executors, and you'll notice that the entry point for all of them is called block on. Well, while sounding like a great Aerosmith song, what does that really mean? It means how your program starts, inverts control, lets Tokio or your runtime take over. We'll have a look at what that really means and how different ways that you can use that to your advantage. We'll take a quick look at what async code actually looks like, how it runs. And then we'll dive right into blocking, which is the biggest scary point that you run into when you're in an async context. We'll have a look at inter-task communication, sending data between channels from one to another, and making sure that your program does what you need it to do, and a few strategies you can use to structure your program to take advantage of that, and also retain lots of yielding so that everything keeps chugging along at a good throughput, even if you're waiting on other tasks. Then we'll look at streams and how they relate to iterators, the basic Rust superpower of combining data, working through it. There's a lot you can do with streams that helps you keep your async throughput going strong, and helps you also continue to think in terms of iterators, writing nice functional code, everything looking good. Then we're going to fire up Axum. Axum is a high-performance web service, typically in one of the top 5 overall performances on benchmarks, built on top of Tokio. It gives you a really nice, easy, ergonomic system for building web services. We're not going to spend a whole lot of time on that. I've actually done some live streams in which I've shown you how to build a web server in 8 minutes. So instead, we're going to dive into some of the tracing features that are built into Tokio and how that can be linked to either log files for the most basic level, real-time htop-like view of what's going on, even linked to OpenTelemetry so that your whole stack can be tracked at once. You can trace the life cycle of an event. And we'll finish with a question and answer. All right, so we're going to get started by having a look at what are threads, what are async code. Now, system threads are obviously created by the operating system. They are the most basic block. Every program has at least one. It has a main thread that the program is running through. And so when you create a thread with std thread and use the spawn function or the thread builder, you're creating an operating system thread. You're calling into the operating system. You're telling it, I want a new thread. It makes a new stack. It links you to the memory space of the program. It's pretty heavyweight. Your stack can be quite large. You're limited in the number you can have. If you have, on my Linux system, when I query the number of threads I could create, I get about 60,000. That will vary by your platform. But because every thread is going to be scheduled independently, the little graphics that's scrolling there is showing that if I had just one CPU ticking through threads, it's going to be... sorry, yes, I am hoping to take advantage of time dilation. Your thread will be ticking one process at a time. And even if your thread is busy, in a lot of cases, the kernel actually has to look at your process, say, yep, still busy, go to the next one. So this doesn't scale very well. If you start having 60,000 customers all connected to your server at the same time, then you're going to get pretty miserable performance because you'll have 60,000 threads, each of which has a stack in place. So your memory usage is getting pretty heavy. And also your timer usage starts to get really quite inefficient because while some threads can indicate, yes, I'm waiting on IO, yes, I'm waiting on sleep, not every thread can do that. They preempt when the kernel decides that it's your turn. Performance will kind of start to grind to a halt unless somehow you found a computer with 60,000 cores, in which case everything's going to be smooth. So the upside of writing threaded code is that you don't really need to do anything too spectacular to use them. You just write regular code. The operating system decides when it's time to change to run another thread. When it does so, it actually makes sure your stack is stored, stores the state of registers, stores the instruction pointer, restores all of that for the next one that runs, keeps going, goes forwards. It's a relatively heavyweight process on Intel and AMD. It's very fast. On ARM, it's quite slow. Now, async is a little different. So we'll start looking at that in a second. So why don't you use threads for everything? Because threads are simpler to write. Well, unfortunately, a busy server with thousands of connections is going to need thousands of threads. You can use the old select system call. This was one of the earliest implementations of async because it's doing basically the same thing. But most of the time, when you're on a server-type context and you're not doing heavy CPU usage, trying to crunch through numbers as fast as you can, most threads will spend most of their time idle. They're either waiting for something to come in over the network, because chances are, unless you are wired with some incredible fiber to every customer, chances are your customer is going to be some latency talking to them, sending data to them, receiving data from them. You're going to be waiting for storage. Your disks aren't instant. If you're using something like an Amazon storage pool, they're even slower sometimes. You might be waiting for the database to finish putting together the data you asked for, running the query, let you know it's done. So your threads spend an awful lot of time idle. The scheduler itself spends an awful lot of time pulling through threads, saying, is this going to do what I need? Is it ready for me? Oh yes, you are ready. Do something. No, you're not ready. Next guy, you ready? Nope, move on. So you waste a lot of time by having multiple threads, unless you've got the workload to justify those threads keeping them busy. Now your async runtime is actually going to be doing something similar, marshalling threads for you, but it's also operating a task queue. And so when you are in async await land, typically a request arrives, you do something for it, and I've got a nice illustration here of the life cycle of an async await. So at the beginning, the request arrives. You have to make a bunch of database requests, request something for Redis. So you spawn all of those off, usually join, so run them concurrently. You wait until they all give you the information you need to give an answer. Your task then goes idle. And so there's a task queue. Your task moves to the back of the queue because you're waiting for all of these other tasks. And then this can be single-threaded. Each of those tasks will wake up, send their request, and they in turn go idle, while whatever they're talking to figures out the answer to what they're asking for. So cycle through. Eventually working your way down, eventually you've got all of the answers. Once you've got those, your task that made the request wakes back up, finishes, say, building the web page, puts the template together, sends it out, and your task is then waiting again because you're waiting for the confirmation that the TCP traffic actually reached your customer. So that's great. Gives you a very logical model. You can break your code up, and you have to understand it's being scheduled cooperatively rather than preemptively. So you're not relying on a kernel to say, yes, you're done, it's your end of your turn, whether you're in the middle of something or not. Instead, it's yielding control when your task indicates that it's waiting for something else. And there is a yield command you can use to indicate that it's okay to let somebody else have a go now. If you're on one thread, though, the danger is that you'll do too much, you'll starve other threads. You'll starve other tasks from being able to run. But generally, when you've got thousands of connections coming in, pounding you, and all of them are relying on connecting to other services, which is pretty common, particularly for web pages, because you're usually querying other services, assembling the data, and presenting it. Then it works really, really well, because all of the queries that are coming in turn into a giant queue of tasks that need to be run. You never know exactly what order they're going to go. That doesn't matter, because you're maintaining throughput overall, keeping your server nice and busy by processing them as fast as you can, one at a time. Now, if you're using one of the bigger runtimes like Tokio, it's running multiple queues, and you benefit from letting Tokio run multiple queues at once. If one CPU finds itself with nothing to do, it can work steal. It can look and say, hey, that other CPU has a bunch of stuff that needs processing it hasn't got to yet. Grab some of it, do it, and you end up with truly superb performance, which is why so many of the top performing web servers wind up being written in Rust. Work stealing is fun to implement. If you ever want to write it yourself, check out the Crossbeam crate. It has a great implementation that's quite readable and quite usable. And so now you've effectively got the same thing as running a number of Node.js instances that as you have CPUs, because you have an async queue on each one. But from the point of view of actually writing your async code, it's completely transparent. You don't need to know about that. It scales it up. It runs really fast. All right, so let's talk a little bit about runtimes and executors. You know the basic theory of what is async. So let's have a look at how it works with Rust. So with a lot of languages, the async strategy is baked in. This is great as long as what you're writing matches roughly what the language envisaged. So most of the time, when you're creating a program that checks a bunch of databases, tries to keep a high-performance web server fed, then that's the set of choices the language made. But you might also be trying to cram all of this down, and you're actually talking to a bunch of industrial control systems, but you need to fit on a tiny little microcontroller. Well, that's not going to work so well when you're using a really large system that is designed to scale all the way out to thousands and thousands of systems. So Rust and also C++ made the decision that they'd implement the plumbing for async. They design it in such a way that async doesn't impose a requirement on allocating memory, so it can be scaled all the way down to tiny little embedded services. And then you leave the actual implementation of the two parts of the runtime, which we'll talk about in a second, to up to the design of a package that will implement it for you. And Rust, I usually use Tokio. Tokio is designed to go big and can also go a little small. But there's a few runtimes that can go down, ditch the whole standard library, and produce tiny, tiny, tiny binaries that you could run easily on embedded devices, but not lose the flexibility of being able to use async to allow you to easily, readily communicate with network devices. It's no coincidence that 5 of TechEmpower's 10 fastest web servers are built on Rust, and 4 out of 5 of those make use of the built-in async system. Alright, so runtimes, what do you have to choose from? Tokio is my personal favorite when I'm building an enterprise project. It pretty much is a do everything high-performance runtime. It's re-implemented large parts of the overall standard library to provide high-performance asynchronous version. And it does this because the runtime works the way we described with queues. It also has a reactor which is basically an event-driven system. This file is ready, this network request is ready, this network request is pending, and its reactor is built for high performance and mirrors the Rust standard library. Async standard does the same thing. It's slightly slower velocity of development. It's moving more towards finding the commonalities that can eventually end up in the standard library. That was its goal. That's why they chose the name. It's always good to have some competition, so Tokio and Async Standard compete for top dog in terms of performance. There's a runtime called Futures that is missing the I/O reactor system, and that's okay. It was originally built as a proof of concept for how to get an executor going. It's evolved into a giant collection of really helpful utilities and a tiny little executor you can use if you're writing a mostly synchronous program, but you've got something that's async that you need to run, put in your program. Futures is a great choice to drop in, run that little async stuff, carry on. You can mix the two worlds that way. Small, SMOL, is worth mentioning because if you just need to cram your async service down to run in something tiny, small is built around that, makes it as small as humanly possible. And there's one called pasts, which focuses really hard on minimizing memory allocations, working well in embedded and also in WebAssembly. So if you're wanting to write in a browser, run some WebAssembly in the browser, but make sure take advantage of the fact that a WebAssembly code can be really fast in the browser, but also not suffer from the fact that WebAssembly threads work differently from Rust threads, and you start to run into a bit of an impedance mismatch when you start trying to use both. Pasts will give you the tools that you need. Now for the rest of this talk, I'm going to focus on Tokio because it's what I'm most familiar with, most comfortable with, and it's probably what you need to actually start making use of Rust in your Rust and async. In your day-to-day workflow, start producing services quickly. And you will find that an awful lot of stacks start with Tokio, add Hyper for HTTP, Tower for service management, and a web server, Axum and Actix being the two most popular ones, typically sit on top. You can mix and match these as you need them. You can go without them and write the services yourself. Tokio is quite capable of letting you go all the way down to the TCP layer if you want and implement your network protocol from scratch. All right, so let's take a very quick look at how you write some async. All right, for the example in the repo, we're using the futures crate, 0.3.28 being the most recent version. I just add it with cargo add futures and let it do its thing. And if you look at the code that we have there, we bring in futures executor block on. So what is that block on? Block on is an inversion of control. You're saying, okay, futures, I'm going to give you the first asynchronous function to run. It's up to you to provide the runtime environment, provide everything that's needed to run, let it run. When that async program exits, then stop blocking, stop holding control, and we'll carry on just like we're a normal synchronous program. And that's found with pretty much every runtime out there, is that synchronous Rust can't by default call into asynchronous Rust. So if you were to just run do work, the function marked with the async tag that's on the screen there, nothing happens at all. It actually doesn't return anything more than a type that's a future. The async tag is a syntax sugar that returns a future specialized to whatever type the function that it's decorating would normally return. And so a future represents a unit of work to be done in the future, hence the name. It's called a promise in some other languages. What you need, and then in order to await on it, wait for it to finish, and if it spawns other things, it in turn can then await for those. We'll look at that in a second. It has to have a runtime to manage the tasks to do that. So you can't execute a future without a runtime. Block on executes the first future. After that, once you're inside, you get access to all of the nice syntax sugar and macros and similar to make it easy to start writing some async code. Now, when you start with Tokio using block on, it's potentially a little more complicated. I carefully put in the code, you don't have to specify any of these, but I've listed all the things that you can specify. So if you can decide up front whether you want multi-thread or to run on the current thread. If you are running multi-threaded, you can specify how many threads do you want it to allow it to create. You can change the size of each of the threads stacks that it creates if you want, so you can potentially shrink things down a little bit in memory usage if you're not going to be using a large stack. You can specify exactly how frequently Tokio will be polling for both I/O events and for jobs that need to be shifted between CPUs. You can specify how many blocking threads it creates, which we'll talk about in a second. You can specify everything, but in reality, most programs don't need this much function flexibility. If you're writing something like Actix, which frequently creates a thread and attaches a whole runtime to that thread, because it's emulating the actor model, then it's great to have. If you're just trying to write some code, get something done, this is overkill, and you can just use the macro. Tokio builds in a macro called Tokio main. Attach it to a main function. You can now make your main function async. You can immediately dive into writing async functions. If you still have the ability to customize it a bit, you can specify flavor a current thread to go single-threaded. If you don't specify something, it builds a worker thread for every CPU that you have, assumes that this is going to be the primary thing that's running, and will do its best to run at the highest possible performance. All the defaults are set for performance for normal usage. All right, so how do you write async code? Once you've got your async context, you're running inside the runtime, it's relatively simple. Every time you want to run a different asynchronous task, you either await for it, and await means suspend my task, add a new task with the function I'm pointing at to the task queue. Most of the time, if there's nothing else going on, that other function will run immediately. Task switching within a runtime is almost instant, and you're not at the mercy of the operating system deciding when to do it. So Tokio immediately knows, hey, this task is ending, let's start the next one. In this case, doesn't do anything amazing, it just prints hello from async. You can also use join. Tokio provides a helpful macro for this, so does futures, and so does std async. We're going to look at the Tokio one. We're just assuming that, and in the full code, there's a function called double it. Very boring, it just returns 2 times the value you pass. But you can use the join macro, Tokio join, hand it a number of async functions to run. They all launch at once. When all of them have finished, then your task resumes. And this is really efficient. If you can structure your program to send all of your database requests that are needed to build the page at once and join on all of them, then you're not going to waste any time re-waking up your task to say, hey, I've got this one, and then sending off another one. You can run them all at once. If you're running multi-threaded, then all of them can execute concurrently as long as the task queues aren't busy. You can also use a system called join all from the futures system. Allows you to put your tasks in a vector. So if you might have a varying set of units of work to gather data to assemble your web page, feed them in one at a time into the vector. Once you've got them all, join on the whole vector. The vector will then contain all of your results. You can pull that out, assemble the answer that to whatever your service is attempting to do. Tokio includes join set, which does the same thing. gives you, I personally think the futures join syntax is a little nicer to use, but the two things that are shown there are equivalent. The Tokio one is a little better at exposing when things went wrong. All right, so that covers joining, which is sending multiple things off all at once, gathering the results, off you go. Sometimes you just want to start a task and you don't necessarily even want its result to come back, you don't care. That's quite common if you say got a background task that's going to be doing something in the background. It might be sitting waiting for messages from a channel. It might periodically be checking that your disk is still okay. It could be anything you want. Flexibility is the name of the game. We're trying to write your program, not whatever I think sounds cool at the time. So in this example here, I'm using Tokio spawn. So I'm joining because you can use, if you choose to wait for spawn to come back, it runs it immediately in a separate process, will return. So running a ticker and a talker, they're launched separately. Each will print tick and talk with a number. If you omit the join in a function as opposed to the main program, that spawn will send the task off to run all on its own. There's no longer a dependency on eventually coming back to the main task. It will just keep on going. You can use this very flexibly. If your program requires that you run several different servers, say a server for talking about an efficient binary TCP system, a server for handling people who connect to you over web-based systems, maybe something to talk to some hardware, you can spawn all of those and have them run pretty much independently, and there's a high likelihood if you're in a multi-threaded environment that they will end up on different cores, but it's not guaranteed. If you do want them to be in multiple cores, you could always spawn threads, give them their own runtime. You've got the flexibility. Rust is built all around being able to write what you need rather than forcing you into a certain pattern. So if you're writing something CPU heavy and your async task is going to pound the CPU, you've got a problem. And that problem is that because async is built so much on the idea that you periodically wait for something else, the assumption is that you need to be waiting for something else. It's cooperative. It's not going to preemptively interrupt you, especially in single-threaded mode. Your program will keep going, and all of those other tasks that are sitting waiting don't get called. And so if you do find yourself doing something like a large loop and you don't have a natural place to call some async code that requires an await point, you can always yield now, Tokio task yield now, and that indicates I would like you to put my process to the back of the execution queue. Come back to me when you're ready. If there's anything else in the job queue, they get a chance to run. If there's nothing else in the job queue, well, you go to the back of the queue, but you are the queue, so you're back at the front of the queue, you just keep going. And so yield now is a good way to break up your code if you have something that just looks like it's going to keep going for too long, but it's not always the best way to do it. We'll look at blocking in just a second for how to do that. The last option that's pretty popular is select. The select macro runs multiple futures, and then whichever one finishes first is the answer you get, and the others are canceled. Unlike threads, it's very easy to cancel futures. You can just stop them. Tokio will make sure that any dropping that needs to happen to free up your resources will happen. But select is great. So here we have a function called sleep random. It generates a random number, sleeps for a certain amount of time. When you run the program, it will select one of these at random, tell you which one returned first. Tokio will run them all in the background. We're using Tokio's sleep rather than system thread sleep to avoid blocking. We'll be covering that briefly. But this is perfect if, for example, you have multiple channels of data coming in, we'll be talking about that, and you want to make sure that you answer whichever one gives you some data first. If you have a bunch of potential data sources, you don't necessarily know which ones are going to be available, which ones are going to be fastest. You can select on all of them. This is what DNS and NTP does. It sends out a request to all of them. goes with whichever one answers first. All right, so blocking. We've mentioned this word a few times. What does blocking really mean? Blocking means I'm going to be doing something that is going to tie up my task and prevent other tasks from yielding. It might be high CPU usage. It might be that the peripheral I'm talking to, I don't have a nice async way to talk to it. I might be doing something really complicated. Either way, you want to minimize the amount of blocking you do. So in the example here is a good example of one of the things you should never do in an async program. Hello delay, when it's spawned, calls system thread sleep for a period of time. And when you run this, you might be surprised to see that even though we're in a multi-threaded runtime and we're launching 5 tasks, each of which will wait for a differing period of time before returning and each printing they start and when they're done, your whole program runs in serial. And that's because Tokio, by default, will be executing your task on the same thread that is controlling Tokio. And so when you pause that thread, you actually pause your entire runtime. And that is a really bad thing to do. It surprises newcomers to async every time they do this. And so that's why Tokio implements almost a shadow version of the standard library. So if you replace std thread sleep with Tokio time sleep and run it, then you get the result you expect instead of saying task 1 is started, task 1 is done, task 2 is started, task 2 is done. They interleave, so it shows you the tasks start, and then you get a gradual task 1 is done, task 2 is done, task 3 is done, and so on. It's very easy to accidentally block like that if you aren't paying attention. So that's one of the things that you need to watch out for, is my task is going to take a while. Tokio does have your back. There's a function built in called spawn blocking. Use Tokio task spawn blocking. And here we have a terrible function, is prime, that is the slowest way I could come up with to check to see if a number is in fact prime. If you spawn this just in a if you check every number from 2 to 100,000 in a non-blocking context, your server is going to stutter because your tasks are taking too long. Other tasks don't get their time slice. So with Tokio, you can always do spawn blocking, and you use it with the same semantics as spawning a thread. And when it's done, you will wait for it, and Tokio is smart enough that it wraps the execution of your blocking task in async await, so your task will nicely sleep until that task is done. So under the hood, your spawn blocking is actually running in a system thread. Tokio is doing the hard work to bridge the two worlds together for you. In your setup, you can limit how many threads it can activate the blocking tasks. Bear in mind that it does run a few of them itself for quite a few I/O jobs, so you don't want to make that number too small. But it's good to see that if you use spawn blocking, ticker will keep saying still alive, still alive, still alive. And that is the primary and easiest way to make sure that you can run synchronous slow code inside your server without having to ever stop using the facade of async, is spawn blocking. Make sure that there's enough work there to justify it sitting in a thread. When it's done, you get the answer. If you want to just attach it, then you can not await it and it'll run separately. And hopefully you've written some logic for its answer to go somewhere useful, because otherwise it just wasted some time for you. All right, so communicating with channels, which is when you have task A that wants to talk to task B. Tokio has a number of channels built in. It mirrors the standard library by providing MPSC, which is multi-producer, single consumer. What it means by that is you can have as many senders as you want and one recipient. There's also a broadcast channel, which allows you to transmit and go to as many recipients as you want to. It's tempting to use it. I've not had amazing results with it of late. So MPSC is pretty much the de facto way, and the way you write the code for this is exactly the same as using the synchronous version, which is well covered. And so you create your channel by calling Tokio sync MPSC channel in the Synchronous world, you do std sync MPSC channel. It's the same. They're deliberately trying to keep the semantics similar. You specialize it to a type. In this case, I'm just sending an enumeration with the option tick. Rust enums let you write as much data as you want in there. So if you want to start sending complicated data between tasks, that's a great way to do it. And enum is a great way to wrap the process. The biggest difference is the constructor makes you specify a maximum queue length. Nothing in Tokio by default is unbounded. Even if you're working with threads, I do recommend putting a bound on your queue so you don't accidentally overwhelm yourself. And then this program spawns the sender, which takes the TX, the transmit channel, and is periodically sending a tick message. The receiver, that is the same pattern that you use in Synchronous Rust to receive messages. So while let, if you have a message for me, give it to me, and call receive. And you'll notice that receive awaits. That's because it allows the task you're in to go to sleep and only wake up when there is a message for you. So sitting there 99% of the time idle, waking up when somebody sends you a message, is very, very efficient because you're not using a lot of memory. You're a small Tokio task. You're hardly using any CPU at all. It'll be practically zero when you get to practical usage. Certainly less than having a thread sitting idle. And so this is roughly equivalent to Go's channel system, with the exception that you don't have to remember to close them. Rust will take care of that for you. I will get to Marcus Payne's question when we get to the QA at the end. So if you wanted to listen to multiple channels, remember we talked about select a few minutes ago. This code example shows you how to do it. Down at the bottom here, we create a channel and then we create a second channel. We create two senders, each of which gets a transmitter to the different channels. And then in one receiver, we just loop forever. We call select, and we select on each of the channel receivers. And the way select works is whichever one gives you an answer first runs. And so if both channels are sitting idle, once again your task won't be consuming CPU. It's just sitting there waiting for a message to be ready for you. Once one of those channels wakes up, tells you to do something, you receive the message on that task. So this lets you build a nice system where you could have a whole bunch of tasks monitoring different things. They generate an event. You can have that funnel into one or more tasks whose job it is to receive those events, send them on their merry way, fan out to process them. So it lets you build a nice little event funnel. It lets you quite easily build an event-driven program. And no, I wasn't trying to diss on Go. I was just I was really just mentioning that in Rust you can usually count on drop to close things, except for the odd occasion that it doesn't. It startles you, and you spend a week diagnosing the program crash. All right. Different channels between threads and tasks are also possible. Like I mentioned, you can use the standard library channels if you want and just use them as you do before to send messages straight into a thread. Or you can do what we're doing here. Whenever you create a Tokio runtime, you can call Tokio runtime handle current to get a handle to the runtime that's currently existing and that you're currently using. And so you can send that somewhere else. And so what we're doing here is we create a Tokio channel. We use standard library thread spawning, make a regular system thread. Now we're in synchronous code. You cannot await on anything. You're effectively stuck if you want to run an async program, if you want to run an async function. So how do you bridge the divide? Well, what we're doing here is the thread is using standard library 3 sleep just to demonstrate that because it's in its thread, it's not slowing anything. It's not slowing your async system down because it's running completely separately. Using handle.spawn, you can actually spawn an asynchronous task into the existing Tokio handle, which allows you to then use the myTX that we created by cloning the transmitter. Transmitter is an MPSC. You can have as many of them as you want. You can clone them all day long. They're designed for that. So your thread gets that as it receives the transmitter as it went into the thread, received the handle. You could even send the handle on a message if you wanted to. And it's then able to use handle.spawn to create a single async context you can put a closure or a function into, run it. It'll run on the runtime that you gave it the handle to. So you're not using block on, you're not making a brand new context, you're using the existing one. This gives you a pattern that is tremendously powerful. You have the ability to spawn threads that are sitting around waiting to do something heavily CPU intensive, and you can spawn a runtime, might even only use one of your cores, be single threaded, to keep the network part of your service really fast, really responsive, focused on getting data in and out. But you feed the data into threads, which do what threads are best at: crunch the numbers fast, get the task done, and then send a message back saying, hey, here's your answer. And so you can get the best of both worlds. Not a case of should I have peanut butter or chocolate? You can indeed have both. All right, let's talk about asynchronous iteration with streams. Hopefully all of you know what a Rust iterator is. They are fantastic. Give you a nice, easy, functional feel for how you can go through some data. So you might have a big vector, you iterate the vector with iter, you map it, you fold it, you for each it, you do whatever you want. Now the problem with running an iterator is that it's very much synchronous. It's not yielding. If it's going to take a while, then you have the downside that now potentially you're blocking by mistake. If you didn't write the iterator, you don't have a good opportunity to insert some yielding. And spawning a whole thread for block on gets, it's a little heavyweight just for that, or even calling into a handle. And so iterators work by storing a type that they will yield and returning the next item with next or none. Well, stream is the same thing, and Tokio stream provides a very nice implementation that you can build on. I built an example there of a stream that acts just like an iterator. If you take away the stream-specific bits of the template, replace it with iterator, it's almost the same thing. And the code here is relatively simple. It just counts up to it just keeps counting up and yields results on the counter. But you can use this just like an iterator, except you're in an async context. So when you go to next, you have to await, and so you can use while let, or you can use a loop through it. You can treat it like an iterator, but because it awaits every time, you are guaranteed to be yielding all the time. So you've kept the joy of Rust iterators, and you've retained the fluency and nice flow and continuation of Rust async. Streams are also really handy if you need to generate data and treat them as a generator. The actual generator syntax has been in nightly Rust development for quite a while. It's not ready yet. I hope it is eventually. But here is an example code in the repo you should find useful for how to write a stream as a generator. I used this in a game I worked on to pre-generate a whole bunch of random numbers because this was a roguelike that used a ridiculous number of random numbers and just keep feeding them out every time you iterate the stream. Once the number was getting a little low, I actually had a thread top up the list. That way, generating the numbers, using them, it becomes self-pacing, generating numbers only when you need them. My CPU usage went way down. Everybody was happy. And once again, because it's a stream, you're yielding every time you access the next element. You don't hog CPU as a whole. If you need to do that, go over into a thread. Tokio's stream helpers system is extremely powerful. You can turn any Rust structure that supports read into a stream. And then, for example, in this example, we open a file using file open. We open a buffered reader. We use its lines feature to load one line at a time. And then if we were loading a very large text file, parsing it one line at a time within our async context, it's quite likely that that's going to be blocking, causing some issues. But by turning it into a stream, we yield at the end of every line, gives other tasks the chance to do something. Don't lose where you are. This example will load War and Peace. You'll notice I'm using single-threaded, but it will still show you chunks of War and Peace coming by on each of the tasks. They never block each other. They keep going. Throughput remains amazing. All right, tracing and metrics. The tracing crate has pretty much become the standard these days for how crates should be logging. When I started talking about this a year or so ago, a lot of people were still using log. Now using the logging crate. Tracing has pretty much become the de facto standard that everybody's using now, at least in the enterprise code I've seen. Tracing from the library point of view is extremely easy. You can just emit log messages, and at some point your program is going to have a subscriber. So the text that we have up here is showing you the long and boring way of making a subscriber, because we let subscriber as a tracing subscriber. FMT, format, we're saying that we're going to use it to format text for output to the screen. We're going to use a compact display. You can customize exactly what appears on your log. In this case, I'm saying show me the file name of the source code, show me the line number, show me the ID of the threads, because you can identify your threads if you want to. I'm not going to have it print the name of the executable, the target that's running. But you can boil that down to just format, finish. You don't need to customize it. The defaults are pretty good. That's one thing to bear in mind when you're writing Rust. Always try and pick sane defaults. That is the Rust way. And so tracing subscriber set global default. Now every library that's feeding events into tracing will be feeding them in unless you specifically override them. So you can do tracing info, tracing warn, tracing error. As you see in the screenshot at the very bottom, info gets a nice green, warnings get a yellow, errors get a red. You can customize which log levels are just being displayed. Format does a great job of giving you data for the screen when you're debugging, starting to write your program. This is the way to go. Even if you're using systemd to run services on Linux, this gives you nice, because systemd traps everything, puts it in your log files anyway, this gives you an easy way to get some logging going. But you may have a more complicated logging system in mind. If you enable the JSON feature in the tracing subscriber, and the code here shows you format.json, once that feature flag is enabled in your cargo TOML, still make it the default, and you log. Instead of getting prettified code, now it's spitting out JSON. And it's relatively simple to, there are crates that will even do it for you to save that directly to a file if you want, implement rotation, do whatever you want with it. If you're just reading the log file and your log file reader prefers structured data, you can do JSON, you can do any other formatting system that you want to implement. And so logging is boring, but it's hard to avoid. It's particularly when you have a big, complicated program. It's really hard to beat having a log message that tells you exactly what went wrong. You may not have had your debugger attached. If you're running a live server, you may not want to have your debugger attached. It's great to go into the log file, see what happened, but it may not give you the big picture. And so tracing also gives you a macro you can run attached to any function called tracing instrument. Instrument is great. You have to enable span events, as you can see in the code that we have there. When you run it, we've told it to emit an entry when you enter a span, and we've told it that we want to know when a span closes. And so when hello world enters, you just get a little note that hello world started. When it closes, it actually shows you the execution time, both busy and idle. You'll see in this case we are sleeping for 1 second. It overshot by 0.01 seconds apparently. I was in debug mode, that's probably why. But this gives you a miniature benchmark system built it right in, and it's very lightweight, and it's linked, excuse me, it's linked to log levels as they come out. So link this to your logging, link this to instrumentation, you can start to see in real time which parts of your program are taking how much time. It's async aware, so you will see idle time for all of the tasks that your items spawn. If they're in turn instrumented, you start getting very granular picture of exactly how long everything took to run. If you're improving your benchmarks, you can, and you still should, use something like Criterion to give you a full benchmark suite to prove that your improvements actually helped. But when you're building something with a view to getting it going, finding the problems, instrumenting spans is fantastic. You can also use macros called tracing span to create a span object at runtime instead of building it in with a macro. So you could check your configuration. Do I even want to be displaying timing? Should I be displaying timing for this section? If I am, then I'll make the span and I'll emit the span at the end. So you have the option there to really customize what it is that you're doing. And so the Tokio project has been working on a project called Tokio Console. There's I personally would tell you it's not quite baked yet. You still have to enable a flag when you compile, indicating that you can use some unstable code in Tokio. I've not had any problems with it. And it can be extremely useful. Cargo, you can install programs with it as well as installing dependencies. So you install the program, Tokio Console. I've used it on Windows, Mac, and Linux. It's all worked great. I have no idea about more esoteric platforms, but it probably works. Then you can import Tokio Console Subscriber as a dependency with cargo add. Replace all of the default subscription with console subscriber init, run your program, and it's listening on localhost to a network port 6669 by default, but you can customize it. You run Tokio Console, and up pops an htop-like display that shows you in real time all of the tasks that are running. You can select tasks, you can zoom in, you can look at a task in detail. I've got an example up here showing you the not just the name, the target, how much busy, scheduled, and idle time it's spent, but it will start tracking the time percentiles for you, start building up a nice latency histogram, giving you exact, 99% of the time we achieved 1.47 milliseconds, but 50% of the time we're at 47 microseconds. So we're doing good. We're doing well with this function, but why is it that sometimes it's taking a long time? If you're writing something latency critical, Tokio Console is a fantastic tool for figuring out which parts of your system aren't scaling well. Because usually when you start seeing longer latencies like that, it means that there's something causing a delay. And so Tokio Console, I probably wouldn't use it in production except for short bursts if you want to monitor some production data that you can't necessarily reproduce. But it's fantastic for debugging, feeding in a debug workload, watching in real time to see what is happening to your program, what went wrong. There's also the tracing OpenTelemetry crate. I did not include an example of that in the repo because you would have to go ahead and set up an entire OpenTelemetry setup on your system, which I didn't really want to talk you through. But OpenTelemetry works very similarly to Tokio Console. You create a tracing subscriber. You tell it where to find your telemetry system. It uses the OpenTelemetry open format to send events for all of your spans. It can send log events. You can combine this all across your cluster, so all of your services are feeding into one place. Now you've got a dashboard showing you exactly how much time all of these things are taking. You can compare the time Rust takes to do things with other languages and crow about how great it was that you chose Rust, or write an angry email to Herbert if you want, saying that we switched to Rust and everything went terribly slow, and I'll try and help you. But hopefully that's not going to be the case. There are tons of different OpenTelemetry viewers and storage systems. This is a screenshot of Aspecto. When you build a Tokio stack and use tracing, almost all of the layers already support tracing. For example, SQLX database will emit timings for all of your queries. Axum, with a little bit of work, you just have to enable some HTTP spanning inside the tower level. Every single query can be timed, and then you can start instrumenting your timing. You can go as fine-grained as you want, you can go as coarse as you want, depending on what you need, depending on what sort of timing guarantees it is that you need to reach. All right, so we are going to end with the topic that probably likes the least about Rust's async implementation. And instead of going deep down into the details of it, I'm going to show you a few ways to get around the problem and also tell you what the problem is. So Rust's memory model is very strict. That's a good thing. You can't write programs that accidentally use a pointer after you've freed it. You can't write programs with data races without putting in some effort. You save yourself, unless you use the unsafe tag, from an awful lot of potential problems. Now the downside is that async, by default, feels a little fast and loose, because sometimes when you have a stream, for example, if you had it relying upon another stream, your stream needs to be absolutely 100% positive that that first stream hasn't gone somewhere else, hasn't been moved, hasn't been dropped, it didn't fail in some way that it didn't tell you about. And so you want to keep that safety guarantee. And so you can ask Rust at any time to pin an area of memory. Most of the time this is implemented with box, the smart pointer type, and you can have box as pinned. Once it's pinned, the Rust memory management system is not going to move it. It retains the address. It's not going to go away until it's unpinned from the wall. And so you potentially lose a tiny bit of safety in the sense that if you forget to unpin it, well, it's going to stick around. So there's a bit of caution required in using them. But sometimes, if you have a stream relying on a stream, you need to pin. If you have a select operation running on dynamic futures, well, those futures might move. You don't know where they are, so you have to pin them. If you're calling yourself, well, that gets complicated. Unfortunately, there's a solution. So let's have a quick look. This is from the Tokio example code. I tried, and I really couldn't illustrate it better than them, so I figured I would just go with what they have. If you have multiple futures, and you are probably generating these through some kind of complicated function, it's probably not going to be something as simple as this, where you're just async logic goes here. The pin macro lets you ensure that whatever you've created in there, until it drops out of scope, is not going to move in memory. And so now you can safely select on both of them, and even though they're variables, they're not compile time, they're not going to move, select is fine. You won't get really confusing error messages. The error messages are getting much better now, by the way. A lot of the time it actually tells you need to pin this instead of something utterly incomprehensible. But Tokio provides a pin macro that makes it relatively straightforward to do this. You just have to remember to use it, and the compiler is going to remind you. So when you want to recursively call asynchronous code, this one tripped me up the first time I started getting into async. I wanted to see how it worked. The first option there, which is a Fibonacci number, this is from the async recursion crate example, will not compile because you're awaiting on yourself. The error message you get is actually pretty comprehensive and large. It fortunately tells you that you might want to try the async recursion trait. The async recursion crate. Crate and trait sound too much like each other. And so if you add that to your dependencies in Cargo TOML, you can recursively call functions all you want. You just have to bring in the async recursion macro, apply that to the function that you want to recursively call itself, and you're still benefiting from lots of yielding. Each of those awaits every time is going to be yielding, so you're still getting wonderful performance, even though you're performing a heavyweight async function. And if you come from functional programming, you probably use recursion a lot, and that's great. And the async recursion crate is the way to solve that problem. One thing that I frequently do is I will have data coming in as a stream, and it's not quite the data I want, so I want to adapt it in flight. And Tokio always calls this an adapter. It's a stream that takes a stream as an input, does something to it in flight, so one step at a time, mutates it, and outputs it as a new stream. And this remains relatively self-pacing because, let's say you're feeding it as a result to a web browser. Well, the web browser is ultimately going to be running at the speed of the slowest item, which is probably the network. So each call to the next entry in the stream becomes self-pacing, working its way through. It's a great model to get just as much throughput as your customer needs. And so I gave you a nice little pre-made example of how to write one of these yourself. What this one does is I created a stream called toUpper. It accepts a stream coming in of lines from a file, just makes them uppercase. But you'll notice there is a lot of boilerplate here. I had to use a crate called pin project lite. It's actually pin project, but I always read project. It replaces a lot of really gnarly, nasty code that you'll never remember and have to look up every time with a much simpler, that you'll probably still have to look up every time, syntax, where you can wrap the thing you're creating, the stream, in a pin project up here at the top. When you create your structure, you mark the item that you want to pin with the pin macro. Again, you're indicating that because I'm relying on this, I need to know where it is. It mustn't go away. And your pull next gains the extra call to self.project, which carefully accesses the pins for you, allows you to write the stream in relatively natural code now. You don't have to have this gnarly blob of code that looks kind of scary. And so that's the pattern I always use for adapting a stream in flight. And that's a very, very powerful pattern. Lastly, I'm just going to touch on asynchronous traits. As Rust is right now, the code on the left there, trait, my trait, with an asynchronous function that's required to be in the trait, will not compile. And the reason for that is that there's actually a whole lot of work required to allow a trait to also have asynchronous functions, because async is really a decorator changing the pattern of the function. Almost everybody right now just uses the create async trait, and because that lets you add that to both your trait and to the implementations. It's a bit of an extra burden. It's worth it though if you are heavily trait based and you like to use that for either mocking or replacing, or just making it easy to stub out or replace parts of your functionality. So you describe the interface with the trait. You want parts or even all of it to be asynchronous. That's the easiest way to do it. Let the async trait do it. The good news is the async working group are working very hard on this. Async functions in traits should be live in stable Rust relatively soon. I don't want to give a date because I don't want to sound like I'm trying to pressure them, but it's coming. It's looking good. The working group is doing a great job, and they're adding a whole bunch of other cool things to async at the same time. All right, as I mentioned at the beginning, wanted you to have the link again. All of the code that we've referenced here in this 1 hour sprint through async, which is a huge topic, but we've tried to dive in and cover all of the major parts, is at the URL on there, which is my GitHub, and then Arden 1 hour async. And now I think we're going to move on to talk a little bit about the next class I'm teaching. All right, jump to the right so as to be on camera. There we go. Feel like singing the time work. So I am teaching for Arden Labs a class called Ultimate Rust Foundations. It is kind of a zero to hero type class. We start with Hello World and what on earth is this FN and println thing. And by the end of the day, of the first module, you are able to write a command line application that loads a JSON file, maps it into strongly typed structures, adds, edits, deletes, the full CRUD stack. By the end of day 5, you'll have written a multi-threaded async server that uses both threads and asynchronous. You'll have been through some of the content here, but in a much longer, more in-depth format. This was, in many ways, a teaser for Module 3, the async section. We are moving to a new format, so instead of asking you to find 24 hours of your time to dedicate to spend with me, you get to join me for a kickoff, join me after each section for QAs, and have video content that you can watch at your own pace, and trying to give you the best of both worlds so that you can do live Q&A with me. I can help you. I'm also available by email. That class is open now and should be starting August 28th. All right, looking through the chat, the first one I saw go by was, what's the difference between Tokio and async standard? And in some ways they're very similar. And sometimes they gripe at each other a bit, but mostly it's friendly competition. And really each has been driving the other forward, that it seems like when one gets a feature, the other gets a feature. They so slowly filter down to the best implementation. So in some ways they're competing. When async standard was created, their hope was that it would become the async standard library for all of Rust. So far they haven't been standardized, but they're doing a great job of working with Tokio and also working with their own users to identify all of the things that should be in a Rust async standard library, so that one day when there is a formal one, as opposed to what we have now, which is a setup where the runtimes implement their own, we know what's there. Now, async standard is very fast, can be used to build really nice, wonderful programs. Nothing wrong with it, it's great, worth giving it a try. Tokio is in the same boat. It's great, it's fast, it's easy to use. Tokio, in my opinion, has gone a little further in terms of adding the features that if you're working in, say, an enterprise development setup, will start to find yourself using, because the Tokio group are obsessive about tracking down bugs, making things run well, and working on more of a full stack approach. So you've got Hyper for HTTP, Tower for services, and so on, all the way down the stack. And you'll find that Axum, Actix, most of the big, well-known libraries are leaning towards having Tokio at the bottom level, as opposed to having standard lib at the bottom level right now, or async standard. Tokio is also, in my opinion, slightly easier to get started with because they have really good documentation. Tokio on Android. I've actually not targeted Android directly with Rust yet. I don't do a whole lot of mobile development. I've seen people talk about it. My understanding is that Rust works very well with Android. I know part of the Android stack has actually been rewritten in Rust now, so I believe it's similar to C++ in the sense that you're producing a library that you can then put into your APK and work with. But I'm not the right person to ask for that yet, unfortunately. So next question was, Go has the concept of closing the channel. Receivers can use this as a way to know the channel has no more data to be received. Yes, there is. There's actually a whole section on this in the class I teach. But Rust has a concept called drop, which is where you, as soon as a variable leaves scope, the drop destructor fires. And this is the same as a destructor in C++, and even the same compiler logic. So so if you are an object, you know that you're going away. And if you are a channel, then you know where your receivers are. So that will result in all of the receivers to that channel receiving a none rather than some and some data. Because when you do while let channel receive, you're receiving some and some data, because an option, which is either some or none. There's no null in Rust, or at least in safe Rust. So once it receives none, that channel's got nothing to say to you anymore, so your receiver can detect it that way. In some cases it is cleaner to actually have a message type saying I'm going away, because you may want to do some additional work if that's the case, maybe before the channel goes away. That's up to you. And let's see, I'm a little bit curious if Tokio will work on Android. Okay, I already answered that one. All right, I think those are the questions I saw go by. So thank you for attending. I enjoyed giving this. I hope that wasn't too fast. You may want to watch it in slow motion, because I was trying to cover a lot of topics in 1 hour.